So as I just been introduced, I'm from MetaMind, and a lot of this work was done joint collaboration with many people. I'd like to particularly point out Kaiming Zhong and Richard Sosha, who are my two co-authors on this work, and to the rest of the team who made research and running these large models relatively easy given the complexities involved. So the good thing is that we all know that deep learning has really gone to a stage that it's simplified a lot of tasks, mainly vision. That's where it's had the most successes over the years, but it's also starting to eat away at text classification and NLP as well. And the good news with that is that with quality data, you can get incredibly high accuracy even though you don't necessarily know all the mechanics involved. So we've heard a lot of talk about the fact that deep learning removes a lot of the necessities of feature engineering. And this is hugely useful for us because we run essentially a machine learning as a service solution. So with MetaMind, you can train your own data set and you just store the data up there. You basically ask it to train and we'll come back later and give you the solution. And the really cool thing for me is that it was so cool, it's so easy to use, that in fact 6th and 7th grade students ended up using it for their high school science competition. They made something called TrashCam, which used MetaMind as a custom vision classifier, but they put together a Lego framework which had a camera attached, and you basically put a piece of trash in the middle of it. It would take a photo and get it classified as to whether it was trash, recycle, or compost. And that was with 90% accuracy and really just kind of student ingenuity. So you could say that we're helping out at the very, very base of academia. But there are many tasks which are more complicated than just, say, kind of ImageNet style visual classification. One of them, which my colleagues have been working on, is intracranial hemorrhage detection. Now that's where you have a bleed in the brain and potentially life-threatening in many cases. And the issue is that I think I was reading the statistics recently of the deaths that are caused by it, about half of them are caused within the first 2 days. So to be able to actually accurately classify and detect this in a speedy setting is a hugely important task. And you can imagine that there are many situations where there's basically a backlog where a handful of technicians are going through these images, having to classify themselves. So the team at MetaMind developed a solution which essentially is able to detect when these intracranial hemorrhages are occurring and provide kind of an alert, a priority message that this person's medical data should be looked at immediately by a professional. So pushing them to the top of the queue so they can get the help that they need. So this was primarily work by Kaiming Zhong, Kaisheng Tai, and Ivo Mihov. But one of the really cool things is it involved 3D convolutions, which is a step up in complexity compared to, say, ImageNet. So the standard neural networks that we've got at the moment aren't a solution for every single task. In fact, beyond classification, as I said, we have the traditional ImageNet dataset, but think of question answering. This is from the visual question answering dataset produced by Microsoft in collaboration with a number of universities. When you actually look at an image, there's a lot of information you can pull out of it, a lot of questions that are involved. So what is this man doing? Is it snowing there? Is the person wearing a backpack? This is a lot more detail than you get out of the ImageNet models. So as an example, if you throw a photo of just a smoothie into our food classifier, it has 500 classes, it's highly accurate, and it, in this situation, gives a correct answer. But what if you're actually asking for something more detailed or a very particular aspect of the image? So this is a very cool online demo provided by a Visual Genome Project, a huge data set that's almost released fully. But you can see that there are so many different aspects of the image that I guess traditional neural networks don't bother capturing yet because they either don't have the training data for it or they don't have the model that's complex enough. Things like the fact that this smoothie is foamy, that there are 2 strawberries next to the glass, that there is green leaves on top of the strawberries themselves. So all of this is information that we're essentially discarding at the moment with kind of ImageNet style competitions. And that was actually a relatively simple image. Imagine you're looking at a field, a long shot of landscape. You might be interested in the bridges. How many arches are there? Or maybe you're interested in the train at the very, very middle left. Maybe you're interested in how many cars are going across the bridge. These are all different things which a human would be able to kind of realize and refocus on immediately, but which machine learning algorithms, because they don't have the data, aren't able to. And another one, pulling away from the visual domain, is textual question answering. If you're given a relatively simple story, Humans should be able to answer this. If I ask you a specific question like, where is Sandra after reading this story, that should be fine. But for a neural network, a lot of the time you're trying to compress all of this information into some tiny space. And it's not necessarily an easy thing to solve. So as a kind of thought experiment, think if I was going to give you one of these tasks. Imagine I gave you an article or an image. I asked you to memorize it. I gave you as much time as you wanted. But then I took it away from you and started asking questions. Now, you're all incredibly smart people, but you're all going to fail. And the reason for that is that you can't store everything in your working memory, and that without a question to direct your attention, you waste focus on unimportant details, or you might not know the specific details you should be paying attention to. A simple example of that would be if I showed you a car, you might then not realize that I'm asking you something specific about the tires or the tread or maybe where the car is sitting. So the optimal solution in this situation would be to give you the input data, give you the question as well, and then allow you to have as many glances back and forth across that material as you would like. And neural networks have the exact same problem. Most of the time, our neural networks, we're trying to force all of this information into one tiny compressed representation. So think of it in terms of an information bottleneck. A lot of the time, you are forcing your model to use a compressed representation. A good example of that is word-to-vec. In that situation, it's actually what you want, though. You're trying to take the contexts of that a word might appear in from tens of thousands of different documents and try and come up with a summary. And the way that it can get around that is it says, well, this word is incredibly similar to this word, so we can essentially compress some of the information about these contexts using that information. But a lot of the time, it isn't necessarily the thing you want. If you've been sitting there increasing the dimensionality of your neural networks, you're essentially playing with this as well. So you should really be paying attention to whether or not an information bottleneck is what you want in that specific spot. And a lot of the time, it actually isn't. So to give you a bit of background just before I get into the main work, we've already had mention of LSTMs and recurrent neural networks, but we're also going to be looking at a gated recurrent unit. Now, it's quite similar to an LSTM. It's a type of recurrent neural network. And so it consumes can generate a sequence, whether that's characters, words, numbers, so on. And the main point to remember is that a GRU just updates an internal hidden state, according to basically looking at the existing state that it has already, and also the input that it's currently receiving. And one of the most fascinating things about gated recurrent units, recurrent neural networks, and LSTMs is that, as I said, they work over sequences, but because of that, they can do some pretty interesting things that traditional neural networks can't do. Specifically, if you feed it, say, a sentence in English, and then try to generate a sentence in French, it's actually able to do that. And the way that it does that is it compresses all of the sentence information into a sentence representation once it's finished reading the English sentence. So the entirety of that English sentence is being compressed and summarized in some small vector, and that vector is then used to generate the French sentence. But think about what we were just discussing before, information bottlenecks. Obviously, really complex sentences aren't able to be captured by, say, a small hidden representation. You might try increasing the dimensionality of that, but it's still going to hit some bottleneck at some point. So as an example of this, the paper Neural Machine Translation by Jointly Learning to Align and Translate actually show that as the sentence length increases, the accuracy rapidly starts falling off. And that doesn't matter if you just throw a whole lot more sentences that are a lot of longer length. The fundamental problem is that you're trying to compress some large kind of space down into a very small representation. So their solution, which was kind of the beginning of a lot of the attention-based networks, was to actually apply attention, allow for every word that you're going to produce, allow the neural network to look back over the input. And the reason that works incredibly well is that, again, it doesn't need to compress all of that information into one small space, but additionally, it can focus on different parts of the sentence at different times. If it was like a one-to-one correspondence, imagine the languages were perfectly similar, it was just, English except encoded, then you would just be parsing one word at a time in a sequence. But French and English obviously have differences, surprise. And the most interesting point to look at here is the European Economic Area in that grid diagram. Now you can see that as opposed to focusing in a normal attention way of the words in sequence, it actually flips the ordering. And that's because the ordering is different in the two different languages. So by actually having a way of allowing the neural networks to look back into the input data, we're able to get rid of the information bottleneck, and we're also able to introspect into the model and see what it's thinking. So the fact that it's actually learned to align between these two languages shows that, well, it's A, doing something quite smart, and B, it's doing the correct thing in the way that it's actually pulling information out of the original input data. So there's a lot of related attention and memory work, which we can talk about if we had more time. But some of the most interesting ones for us are memory networks and end-to-end memory networks by Weston and Suktaba et al., mostly based out of Facebook. And their work is basically summarizing, say, a number of sentences into these input representations and then paying attention over that. Because for us, we're really looking at a way of doing a flexible question answering framework. And what we ended up calling down on was dynamic memory networks. The idea was to have a modular and flexible framework for question answering that we could swap out components as needed. For full details, you can check out our two papers. They'll give you a lot more detail than I can provide in 30 minutes. But the general idea is that each of these components has one specific goal in the neural network. And because we can swap out the input modules as we might want, we can decide to, say, do a text task just by swapping out the input module, or do an image task by putting in a convolutional neural network. One of the other interesting things is that it can actually be generalized beyond just question answering tasks. We've shown that the dynamic memory network can be used on things like part of speech, named entity recognition, sentiment analysis, and more. Just because I guess there's an implicit question in that, rather than a question that changes depending on the context. Now, there are 4 primary components in the dynamic memory network. The first, as I said, is the input module. It takes the input, converts it into a vector representation. The second is the question module, which does the exact same thing, but just for the question. That's relatively simple. It's usually just a recurrent neural network. The third is the episodic memory, which is responsible for 2 different tasks. It's responsible for looking over the input and working out where to pay attention and what information to extract, and then updating its own internal memory as a second step. It can do that multiple times and hopefully come up with a correct answer by the time it gets to its end state. And the fourth and final component is just an answer module that takes some sort of vector representation as input and outputs, hopefully, the correct answer. So the input modules are kind of a really interesting part, and it's one of the most, one of the focuses of the paper that we recently published. And the reason for that is that obviously, when we want to tackle different tasks, there are different things we need to do, specifically differences between, say, textual input and image input. So for textual input, what we ended up doing was having a sort of hierarchy. So for sentences, we basically read a sentence using some sort of sentence reader, whether that's a recurrent neural network, some sort of linear scheme, it doesn't really matter, as long as it gets a representation of the sentence that has the information that we're interested in. So once we've got a number of those, we call them facts. And then we apply what we have as a bidirectional GRU, referred to as an input fusion layer, because it basically shares information between the different facts. And it also adds ordering information as well. So the fact that one sentence comes before or after another is important information. The fact that 2 sentences might be discussing the same topic and should have information shared between them is also an important consideration. And so after that input fusion layer, we also have these facts that have both local context, so what their one sentence was about, and also global context of what other sentences are doing around them. The second one for visual input is quite similar to normal convolutional neural networks. So you take a normal convolutional neural network and then you kind of cut it off just before the end. So the representation there, or kind of mental idea, is that you split an image into image patches, you run a convolutional neural network over those, but you don't end up mushing all of those image patches together to a final single vector representation. So you then can take those image patches, you can traverse them in some sort of fashion, whatever you'd like. We use a snake-like pattern. And then do the exact same thing as we did for the text. Run an input fusion layer, so a bidirectional GRU, that shares the information across these different image patches. That's important because you could imagine if a single object goes across multiple image patches, that's information that should be shared. So with the input modules, we're primarily looking at producing an ordered list of facts, so just vector representations from the input, And we can control how much information is lost or retained by either increasing the dimensionality of the vector representations themselves or the number of facts that we have. Some of the other work, for example, instead of doing sentence-level extraction, does word-level extraction. The second part, and kind of most complex, I guess, for our work, is episodic memory modules. And the idea is that it's composed of 3 parts. It computes attention gates over those facts that we just produced. It has an attention mechanism that basically pays attention to the focus that we already have and works out how to extract the information from the input data, given that information. And the third part is it updates its own internal memory state. So for the attention gates, each and every one of the facts that we just produced from the input module receives an attention value from 0 to 1. The values are produced by looking at 3 different things: the fact itself, the query, and also the episode memory. And it's important for the episode memory to be paid attention to because some of these tasks involve transitive reasoning. The original question might not have all the information you need in order to get the correct answer. As an example of that, if I asked where was the apple, I might realize that John has the apple, and then I need to work out where John is. So the question kind of evolves over time. So it's a normal kind of 2-layer neural network, and at the end, we can also optionally enforce sparsity by using softmax over these attention values, so ensuring that all of the attention values sum up to 1. And that's important because the traditional attention mechanism is something called soft attention. And that's just a weighted summation of all of the input facts, depending on what the attention value is. If all the attention was paid to a single one of those facts, it's essentially just selecting one fact from the input. The issue with this representation, though, is it actually loses 2 different things: positional information and ordering information. You can kind of lazily or cheatily extract it by running many, many passes over the input, but that is essentially O(n) over the input, so not a good idea. So what we ended up turning to was actually creating an idea, modifying the GRU, and producing something called an attention GRU. So I won't go over all the equations now. It's a little too detailed for a quick presentation. But the important thing to realize is that a GRU has an update gate, which tells you how much of attention it should pay to the input that it's receiving at that moment. And the update gate is, in some ways, a form of attention itself. Issue with this is that it only is able to produce that update gate by looking at its own internal representation and also the input that's got access to at that very moment. It doesn't have a broader idea of what the query might be or what the episode memory might be at that stage. So we can actually kind of inject that information into the GRU by replacing the update gate U with the activation gate G that we just produced before. So it has additional context, and it can hopefully make better decisions as to what it should be paying attention to. So again, basically it's got those 3 different components. It produces attention over the image or the text and works out what to pay attention to. Then there's an attention mechanism that extracts a context vector that hopefully has the next chunk of information that's important for you. And then it updates its own internal memory state using a memory update mechanism. And all of this helps getting past that information bottleneck. If it's a very simple question, you might only need 1 iteration. If it's a complex question, you might have multiple passes of episodic memory that hopefully ends up with the correct answer in the end. So for our results, we primarily focused on 3 different experiments. The first was text question answering, the second was visual question answering, and the third is attention visualization, which helps you actually understand, I guess, where the model is looking and provides you the ability to introspect the model for interesting characteristics. So for text question answering, we used a data set called Babby, which was produced by Facebook's AI research team. And Babby is composed of 20 different components, all aiming to capture a different element of logical reasoning. It has time reasoning, it has transitive reasoning, it has a number of different tasks that are essentially stepping stones to the idea of an intelligent tool that would be able to perform a lot of these different tasks. This is a visualization of what the dynamic memory network actually looks like when being run on one of these questions. The question that's given is, where is the football? And across all of the sentence, there are many different things taking place. There are many different people doing different actions. So if you were trying to represent this using a normal deep learning model, you'd usually end up running into that information bottleneck. But instead, in this situation, we know that our key piece of information to start off with is football. So we're able to find basically the one sentence that has the football in it, which ties you to John, because John had the football. And so in the second pass through the episodic memory, we can actually just pay attention to the fact that where is John in the last situation before he had the football, and he ends up being in the hallway. So for this task, we actually ended up doing better than Facebook's end-to-end memory network representation across a number of different kind of tasks. There are some interesting surprises. One is basic induction. It's actually an incredibly easy task for a human, but both Facebook's model and our model failed kind of horrendously. So we're not all the way there, but a lot of these do require multiple passes over the input. A lot of these do end up having stories of 50, 60, 70 sentences in length. And so it shows you that you're able to actually work out these kind of complex tasks and the machinery required for these complex tasks using just simple question-answer pairs. Because none of these are given additional information. You're given a huge story as the machine learning model, the question and the answer, and nothing else in between. One of the more exciting ones, and work primarily done by my colleague Kai-Ming Zhang, is the visual question answering angle of dynamic memory networks. So this is a task of visual question answering, essentially a competition that's still being run. And at the moment, the DMN has kind of state-of-the-art accuracy across the different models that are being tested. And again, one of the reasons for that is that all of the models other than SAN actually use a standard convolutional neural network where you take this huge image and try and compress it down to one single vector. So you end up losing a lot of information that's necessary for different questions. And we can actually see that if you look at the different summaries. So there are 3 different types of questions: yes, no questions, other questions, which might be like, what is this photo of, or what's in the background, and number questions, so usually counting questions. The dynamic memory network does substantially better than all of the other ones at the other questions. So usually questions involving detail, involving complex questions that don't have simple answers. Whilst the other networks, it's competitive with, but the other networks which summarize the whole image down to one single vector representation do basically better on the number task, so the counting task. And the reason for that is that there's a complexity involved with traversing these image patches and making sure you connect them correctly. You can imagine if we're asking you to count the number of, say, flags in the photo, and a flag goes across multiple image boundaries, that's a problem. But one of the most interesting aspects for this is that with these attention mechanisms and memory mechanisms, you can actually see what the model is thinking, to some degree at least. And so even though we've never taught the machine learning model what the concept of the wild is, so trees, bushes, lack of human infrastructure, you can see in the image in the bottom right, the focus is paid just to, say, the fences, to the building in the background. And actually ignores the animals because that's, I guess, positive, proof that it isn't in the wild. Is in the wild, sorry. Another one is the how many pink flags are there. It pays attention to exactly the part of the image where the 2 flags are, and luckily outputs the correct answer. And what type of trees are in the background? Pine trees, and it just highlights that area. It can get even more complex than that. For example, what is a boy holding? The concept of holding isn't, I guess, it's related to a number of different things. But in this situation, holding is related to a person. And so what is the person holding? We're particularly interested in what they have in their hands. And so it highlights the person's hand and also the board next to it, which you could also imagine is complex because this kind of holding is different to if I was actually have it kind of under my arm. And for me, one of the kind of really, really fascinating aspects is, did the player hit the ball on the bottom right? You can actually see that it highlights not just the person standing there, but also, if you have kind of good vision, the ball in the very top right corner of the image as well. So it is really paying attention. It's looking for a ball, and it's looking for proof that it was actually hit at that moment of time. And so all of these sorts of things would end up being lost if we were just trying to compress all of this down to a single vector representation. It's only because we're able to look over the input facts, we're able to inject the question into the model so it knows where to pay attention to, are we able to actually kind of get these good results and actually see the work that is involved. So in summary, attention and memory are hugely important things. I think we're going to be seeing a lot more of them in the coming years because they can avoid the information bottleneck and they can actually capture a lot of different complex logical reasoning tasks, things that might require multiple passes over the data in order to solve. Additionally, we think the DMN is a flexible framework for a lot of different question answering tasks. We've shown that it works for both text and vision. We could theoretically try extending it to audio as well and expect hopefully these same results. And the main idea is that as we keep improving this one framework, we might improve, say, the speed at which we're able to do episodic memory. We might be able to outsource the input module to BidMark. And a lot of different other things which you're able to do when you kind of modularize your framework in this way. And finally, attention visualization can help in model interpretability. As you saw in our examples, you can see exactly whether or not the neural network is able to work out and pay attention to the correct things in the image, and actually see that what you're hoping for output is the correct thing indeed. So thank you guys very much. I'll put this presentation up online, and if you have any questions.